is required. If not, we could get started with today's session. And this time we'll be walking you through robotic subtraction techniques. So we'll primarily talk about CNC milling and 6-axis milling. So we'll start with a few examples, run through the script, and see a bunch of videos that will hopefully sort of give you enough insights to almost imagine the machine this time, because instead of a static machine, this time the end effector is actually a rotating drill bit, right? So it's hard to imagine that without it actually being in our Rhino space. But yeah, hopefully this should orient you well enough. So before I share my screen to show the examples from all you guys, do we have any specific questions, troubleshooting with any of the scripts, or was it fairly straightforward? Is that a thumbs up? Okay, perfect. So super. Yeah, that's really helpful. So let's just. All right, there we go. Can you guys see my screen now? Okay, so let's just go through a few examples. And even while we're doing this, I think Sarah and I both, we'd like the first 10 minutes to be slightly informal, just talk about your insights, or as we go through the slides, if each of you guys could just talk about what your experience with this first assignment was, or a few hiccups that you experienced, that would be perfect. So do we have Muhammad? Yeah.
Hi.
Hey.
It's me.
Perfect. How's it going?
Yeah, good. Thank you so much. So here, what I was trying to do is yesterday, Sarah demonstrated like the hexagonal plane, which were like in YZ plane. So all were in a single plane. So the robot movement with all the curvature should be like, linear, and the same axis will rotate. But here what I'm trying to do is along with like moving the plane, I'm trying to rotate it as well in a perpendicular section. So I just wanted to check the trajectory, like how things are moving. You can see in a demonstration, I have taken 3 points, and in all of those, all the axes are moving. So all axes are different. All those things. So that was the basic idea actually.
Perfect. And even while we go through this, yeah, absolutely. If you experience hiccups with your geometry being too large or the axis not sort of reaching it, feel free to talk about that as well. Just so,
yeah.
And these are really common. So I think people can really build on your experiences.
This is someone else's.
All right. Are they with us, or we could move on?
Yeah, this one is mine. When you guys showed us the Shakespeare example of how this light works, I was very inspired by that, and then I wanted to create something with shodo, which is like a Japanese calligraphy art. And I wanted to see, because shodo means like the way of writing, I wanted to see how we can take that ancient art and make it with, or recreate it with robotic structure. And because it's a way of writing, there is like a certain way to write it, or like to create these characters. And I experienced different ways of writing with the Kuka, with the Bianco, let's say. And
it's really nice to just hear that people are familiarizing to it. I thought it was just Sarah and I just obsessing.
Yes, and yeah, I changed the axis and the curves, the amount of curves. And yeah, this was like the last attempt of mine. So yeah.
Perfect. All right. So I don't know if we have, is that Vahid?
This work for mine, and I start my work from the simple shape on the right image GIF. I create a box and attribute to him populate 3D for random point, and then I use the Voronoi 3D. And this path come from the Voronoi middle of each point on each object. In the middle GIF, I use the dendro like a fractal object, and I use the path to this shape. And the last, I concept this from the sticky figure, and I create the path like that. It's my work.
Yeah, no, that's really great. Even the image on the left, I'm curious to see if any of these toolpaths cause like instances of singularity, or if the axes turn pretty seamlessly. So I guess we'll wait on Will Lab to help us out with that. But it's great to see these animations. Even I think you guys are getting a really good grip on even communicating about 3D space with 2D images and diagrams. So that's amazing.
Thanks.
Okay, so this one is mine, and as you said, to opt for something rather simple, I tried to find a shape that could be parametrically modified, but simple, and I thought of a kind of light tunnel, which could be modified to look more like a flower. Sometimes I think if I lofted the curves in the last variations, it would look like one. So yeah, I just created a series of circles, smaller and smaller, and then turned them to a more shaky variation. And the shakier it gets, the more messy the outcome is in the end.
Yeah, for sure. Or also just starting with the fact that it's completely sort of random points coming together, which also means every time you change the parameters, you come up with a new geometry. So you wouldn't have necessarily modeled it out. And that's one concept we'll sort of dive into today as well, when we look at sort of the robot trying to give you an output with certain line inputs that could potentially change. And we'll talk more about that, but thanks so much.
And Misri, can you come back to the previous slides? Just because I have...
The one?
Yeah, that's the one, because I think... So one question, did you submit like more than one file? I don't remember, like for us to do the light bright?
No, I submitted just the first one.
Why don't you export 2 or 3 of them? It really would be interesting.
I thought that we could export only one, like you could process only one, so I can send more.
Yeah, I mean, let's try. Let's start with one, and then maybe if we have time at the end, I really would like to see the iteration and to see like the work that you... Yeah, right. The work that you have done in with the digital twin, to see that in reality as well would be very interesting.
Would be amazing, yeah. And I had this one problem with spline, like it's me.
I know. I remember. So that's the thing, right? The spline is actually the best kinematic setting to carry out this exercise based on your file. We cannot do that. It's just a technical issue. I just couldn't
see the difference between the two other well, so I was wondering how to solve it, or is it just the way it is?
So sometimes it's, in Kuka PRC, the toolpath that you see is an approximation. And so sometimes some tweaks, you don't really see them as a preview because it's just machine calculus computation, let's say. So you don't have like the fully the control over that, but like it's close enough. Yeah, let's try. So I changed your mode into point to point. It would be interesting to see this iteration. And I have one question, just because like I went through your files, guys, like real quick, but did you use any did you randomize any input parameter?
Yes, the vectors that change the points on the circles are randomized, and yeah.
Yeah, I think so. We always have conversations about this notion of random, because sort of Grasshopper allows you to play with random, and sometimes to me, like when we have conversations in final reviews, the discussion that comes out of that is it fair? Should we do that? Do we have control? Do we have authorship over certain things? And then, like doing more research about this notion on using computational design in a creative way, came across an interesting reference from Vera Molnar. You guys using Grasshopper, you might know her, like pioneer of computational design, like in an analog way. And basically she said, what she states is the fact that like random is just like create a multiplicity of outcomes within certain ranges that you decide. So like you have certain inputs, and within like that range of inputs, you create randomness, but like you still have control over that. And I think that you're demonstrating this. Like this was an old story, just to say that like I see that you are showing how you're tweaking your intentions through this iteration, which I just think is fascinating. Yeah, and let's try to take more pictures of this.
Yeah, for sure. And just the notion of authorship in computational design is also so blurry, because it isn't sort of like starting with one person, but instead you're also relying on, like even like just like Grasshopper or other plugins, they're sort of curated by someone else. So there's always a blurred definition of authorship in general with this kind of work. So yeah, just crediting people in the right way is definitely the safest way to move forward. But yeah, this is just a side note. But yeah.
Yeah, and like faculty members and experts and theorists are fighting about this, like whether we have or not authorship over certain procedural aspects of computational design, and I love it. I love when they fight. So what's next?
Miriam, do we have her with us? I guess not. All right.
Hi, this one is mine. I think the left picture, the left GIF isn't shown. It has a large size, so maybe it's because of that. But as you see in the diagrams, there are 4 circles with random rotation in the space. And I divided the circles and just randomly connected the dots to create a 3-dimensional model. And I think it's really a great use of the 3-dimensional potentials to just create this light printing with robot. And yes, now the left GIF is showing. That's it.
I think what's funny is that like in the previous days of the workshop, days 1 and 2, like we explain certain things in a very basic way, like with the maze, for instance, when I mentioned, I'm assuming that you guys can draw a polyline in Rhino, and you guys are way more advanced compared to, you know, like the purpose of the workshop in terms of computational design, in terms of Grasshopper, like let's say generative design, which is awesome because it makes me think that you won't have issues by like increasing the difficulty of the scripts, starting from like today's work that Misery will show, and then keep going on like the objectives of the hotwire cutting, and then going like we really have like there's a high bar now, like for a high expectation, like to see what you guys will come up with in terms of imagining a customized robotic process in architecture. I think it's really promising to see that you have these skills, and we can just push our creativity further now that we know how to, you know, to work with Bianco to use a robot.
Yeah, definitely. I would echo what Sarah just said. And also just the fact that you guys are sort of imbibing this so quickly that I wouldn't be surprised if, I mean, I'd actually love for you guys to sort of come up with examples that you think are really interesting and fascinating so that we could have a slightly more fruitful discussion towards the end of it once we're trying to wrap up this entire conversation about robotics. But also if you guys don't agree, that would be perfect because then we'd be debating. So I think that would help. All right, do we have Jonathan with us? Okay,
hi, I'm here. Yeah.
Hi.
In this, I was kind of looking at and kind of explaining the idea of layering as the robot kind of draws the light image, kind of with the idea of the long exposure that after the first kind of, here I have a kind of deformed sphere in the center. Once that's kind of drawn, then it looks like the robot's kind of drawing around this object that's already existing in three-dimensional space.
That looks like a lot of lines. Did you have any hiccups with having to, well, maybe this is just simulation, so everything is perfect on the screen.
And also the lines are piped. So that's, I had the same, so when I open it, I'm like, oh no, are there too many points, but actually it should be fine. It's pretty neat, the geometry, and I think it's, in this case, you played with, actually you deployed regularity, like a very regular pattern. And again, this comment for everyone, really just successful to see how you use the three-dimensional space and try to see really how to occupy X, Y, and Z and rotations for this exercise. So I think that's another successful example. And I think we'll be able to process it soon. And I'm really curious to see what happens when, like in those, there's, you know, there's room for predictability in the implementation as well. So they're really curious to see, you know, what happens in those moments in which we have more density toward the center of the geometry, and see there, like if the robot will slow down or no, and really appreciate also like that unexpected part of producing a script. So
yeah, for sure. Also with the kind of geometries and the depth that comes with it, I think you're really leveraging the fact that the closer you are to the camera would probably mean the line is thicker, or like or the other way around. But yeah, it's really interesting to see that it's being considered. All right.
This is mine. I actually wanted to experiment how rotating around my geometry in space would look like. So I kind of made the animation revolving around that. Actually, our intention is basically capturing it from the front view, but I wanted to experiment that too.
Yeah, the camera angles are definitely super interesting, and it's, I mean, I'm always intrigued by the fact that sometimes in like shooting movies or like photography, cameras on a robot, in the past couple of years, they were really trendy just because it plays with certain kinds of perspectives and at the same time sort of really gives you this precise, pristine control over the way the camera even moves. So I think this is really well curated.
Yeah, and you made me think like having like this kind of visualization. It's kind of like a meta project in which like I was imagining really a robot with the camera revolving around our robot doing the toolpath. So, and I don't know if you guys are aware of this, but this made me think of, you know, like some startups like Bot and Dolly, I think it's one of the names that are deploying robotics in for the like for to shoot movies in the entertainment industry, and I think that this combined to other technologies, to VR and AR and projections, I think is just an interesting combination of, you know, like these technologies coming together, and again, like this back and forth between architecture, design, and entertainment, and back, you know, like starting from like we got from the entertainment industry, like the renderings, the visualization software, and many of these things, and like now in design, absorbing robots from the manufacturing industry and giving them to the entertainment industry to, you know, to shoot movies. I think is it's just an interesting way of sharing knowledge, intelligence.
No, that's a really good point, because even like all our forthcoming examples, it's intriguing to notice that their teams don't just consist of architects and designers, but instead like mechanical engineers and material scientists and industrial designers. So I think this definitely sort of keeps the conversation going in terms of blurring the boundaries within the discipline and sort of, in a way, sort of shattering the definitions of what architects are supposed to be. And that opens up this whole avenue of debates and discussions.
So who's next that wants to share some thoughts?
Yeah, hi, this is Mai, actually. Sorry that I wasn't able to upload any files to the drive because the access issue. I emailed you the files. But in terms of this design, it's basically that I generated a rather complex yet extremely symmetrical shape that I think it might be very interesting to alter the axis, to misalign the axis of rotation, the axis of symmetry, and the axis of perspective to create a false illusion of irregularity. And basically that's what I did by cutting off 75% of the shape while rotating it 3D. And then simply cutting through it with a contour that's also misaligned with the axis to somewhat expose the interior quality of this shape. And because of that, my computer was actually not able to handle the full simulation, so I wasn't able to export, you know, the animated version of this toolpath.
Yeah, the geometry looks fairly complex, which is why I was curious if this was modeled in Maya, because it's like screaming Maya right now. And it's so organic. Do you want to talk through some of the modeling processes?
Yeah, and actually I'll be curious, I'm adding one comment. I'll be curious to know if you model this form just specifically in the context of this workshop, or this comes from, you know, like other design processes, because like it seems like you have a sense of like 3D and physical object, and I'd be curious to know if you translated this from like, I don't know, a previous process, a previous concept.
Definitely. So basically the shape was made particularly for this workshop, but the process was rather simple because there was a plugin that was utilized called the Launchbox. It was able to create some math surfaces in a rather simple processes. And out of that, it was just several attempts to make sure it kind of meets my expectation. And then I get this shape.
Yeah, no, that's perfect. I hope you can run it. I don't know if this means bringing down the points, but that also kind of means we're losing the resolution, but we could definitely give it a shot and see what comes out of it. All right.
Yeah, I think this is the last one.
Oh, perfect. Do we have Tirulok with us? Am I saying it correctly? I'm sorry if I missed
so.
Okay.
Yeah, we cannot hear you. I don't know if you're talking or if the mic doesn't work.
I know she's with us.
Yeah.
Can you hear me now?
Yep,
go ahead.
Perfect.
This was just an experiment with the shape, and I tried using the heart one with the actual curve of the heart, but it did not work that way because the points on curve was detecting just the 2 points within the heart. So then I tried having kinks in that heart itself, which represents the heart shape. It's just a simple experiment, and this one is the left side one, populate geometry one, and I tried using a curve. Then I later changed the degree of the curve to lines, and that's it. Yeah.
That's great. I also see a lot of you have like extruded a circle or something to like add thickness to it. I think that totally makes sense in this context.
Yeah, and also again, like trying to show the motion in like as many ways as possible. And yeah, it seems that it's interesting to see like how you're trying things, and you freeze the robot in a certain position because maybe you consider that relevant to explain what's going on, what comes first, what comes next, and then you try things and you try a loop. I mean, that's a great place here to try things and really like to deploy these methods in the context of robotics. And to me, it's interesting also is like I don't know, guys, about. I really would like to have a whole day with you and just talk about like your background and to understand like what are the projects that you developed in the past. But it's interesting to see, especially like this past semester, in which with students at COED, I approached them using direct modeling and Rhino, and then generative modeling and with Grasshopper, and then Gravity Sketch in a VR environment. And you can tell that like the students are different, and like maybe those that don't like too much, I don't know, working in Rhino, they shine with Grasshopper, or like in Gravity Sketch. It really depends. You can explore different workflows, and then you figure out that you're very good in one specific because it's just how your mind works or your creative process works. And I think it's fascinating to give like to expand these opportunities, so like that really the designers can find their own way to express their creativity in the best way possible. I think it's just great. So yeah, it seems that you guys are all sort of generative design oriented, and that's great. And hopefully with robotics, you sort of like you're taking this a step forward in terms of like imagining also time and space. So like not only the geometry in your computer. that's exciting.
Yeah, there's also something this tactile nature of jumping between 2D and 3D, and now I just found out Photogram is also available for like phones and in form of apps, so that adds another dimension of AR VR with our modeling software. So I think that should be, I mean, I think towards the end of the workshop or like day 5, I'd also be interested in what sort of got you guys interested in wanting to explore robotic fabrication, or just to sort of close the loop also between generative or computational design and fabrication, because now with numerically controlled machines, the loop has really sort of closed, because it's almost like a feedback system of some sort where you could really prototype super rapidly and sort of take the conversation ahead with your fabricators. And we're hoping the next 2 days sort of really helps you not just talk about geometries and 3D modeling, but also materials and processes in general. So if we don't have more comments from the students, we could just jump in and compare this process to our previous assignments. And in a way, what we'll be doing today is also gonna rely heavily on sort of imagining the process, and we'll sort of get oriented with this process where this was actually the setup at Ballard International when I was serving as the fellow at Lawrence Tech. So what you see in front of you is this reclaimed 6-axis, I think this was a KR 150, so it could very easily pick up a car if you wanted it to, if that helps with the scale. And on top of that, we had a servo motor, which essentially houses a drill bit with a collet right there. And the drill bit here sort of rotates at varying speeds depending on how you sort of set the speed in RPMs or hertz, or either way. It basically rotates drill bits. And that also means every time the robot moves, it starts to sort of consume the material, as against 3D printing, which is primarily like adding material, and hence we call it additive manufacturing. So I'll write
one question. I'm curious
Yes.
to know, was the robot that you used a second-hand, a used robot?
Yeah, I think it came from a Ford facility. But yeah, there's also like this, maybe actually Fanics are used in Ford. So maybe this came from the Mercedes plant in Alabama is what I want to say. So basically, just to give a quick overview of what's going on with Ballard, is it's a company that buys and sells robots and sort of finds like foster parents for used robots. And in a lot of ways, it also sort of makes robots more accessible. And there's this notion of how expensive and it's hard to get your hands on a robot. So it throws this question in the air and tries to grapple with a few of how the industry works in conjunction with production industries. And just the way robotic fabrication is catching up, it's also hoping that it becomes slightly more available instead of, so it talks a lot about access and just larger notions of getting access to these machines, which is interesting. So I mean, I actually should have included one of those pictures. I'll be sure to do that next time. But I think Sarah has visited the facility, and just imagine a warehouse with about 3,000 robots just hanging out, doing its thing.
Was the end effector used as well, or that was a brand new?
The one I just showed?
Yeah.
Oh no, it was used.
Okay, so
they had to sort of take out all the previous end effectors, really erase its memory, and put a new end effector. All right, so through the course of this presentation, I'll primarily walk you guys through some of the histories, just to orient ourselves with when numerically controlled machines sort of came in, why they came in, and sort of what that, so in a way, threw us into. And I'll sort of end with a few contemporary research practices, which and they're really leveraging the use of robots, and also share some of my work and a few videos. So that should hopefully walk you through the basics of what the system is, right? Because we're dealing with two things today. One is the robot, which, I mean, very evidently you guys have a really good control over. But secondly, it's also sort of taking the concepts of a CNC milling machine, right? So we'll talk about a few technical things, but just feel free to stop me at any point so we could elaborate on that a little more before we jump into Rhino and Grasshopper. Perfect. So these two images in front of you are from when this idea was first conceived, and the idea of numerical control. What you see on the left here is while making actually blades for choppers and stuff like that, they would almost always have to fully handcraft the panes, which also means precision is not up in the air because they were really skilled craftsmen, but that also meant more wait time to make every piece. And that was the first time they tried to sort of use a motor to just move the piece up and down, which could in a way use code or like a 3D coordinate system to move the objects. And even if you just question the fact that this was happening in 1940s and 50s, it also puts us in a not us, but at the just the way people worked back then to code. It wouldn't be as simple as just opening up Python and just writing out code, but instead they worked a lot with punch cards. So they would have to literally punch out holes on a punch card, put them in a series, and that's how the code was run. So it was a tedious process, but once they realized that the repetition and the motion that was a part of it was repeated so many times to make the exact same piece, that they decided to put a drill bit right here, which is where my cursor is, and decided to connect that with a motor that could be run in one axis. So this is the very first iteration of this process. And it also, oh wait, do we have something going on? Oh, I see. Okay. Just I haven't kept an eye out on the chat, but if something, just feel free to jump in at any point. All right.
Yeah, I'll moderate that, Misra, don't worry.
Perfect. Yeah. All right, so moving on, this is cut to 2016. And what's interesting, I'm just going to toggle between these two images because this project is one of my favorites, and just the way they've sort of leveraged the fact that it's a rotating circular disc running through stone. It's subtractively sort of taking out the material to make about, I don't know, 399 bricks is what they claim to be. And I mean, since it was in Venice, I really hope, Sarah, if you visited the place, you could throw in some insights, because now what we're dealing with is machines invented for the sake of repetition, for the sake of production and technicality, versus machines being used for design and computation and architecture and spaces. And this
not only that, and constraints as well. It's like
absolutely.
Right, like the design constraints, but also the surrounding environment. And so like the challenge here was really to push the design, but also take into consideration the site and like the exhibition logic as well. So I think it was just, and the scale as well, because it was, I don't know if you have ever been, guys, in Venice, to the Venice Biennale. This was in the Arsenale building, and it's basically a long path, and you go through, like in each big room there's like you can go through an exhibition or a pavilion or installation, and that was just so impactful because it brought together like so many things. And yes, and as Misery said, it's just like a celebration of technology and experts coming together and producing this.
I haven't actually been in the space, but from what I've been told, if you imagine all of these just sort of standing or well nested on top of each other, held by just compression, I think at first people were even scared to go under it because you're just standing under tons of stone weight. But I can only imagine how nervous Philip Block would have been before they took all the support systems out. But yeah, so this process mainly highlights a circular disk right there, sort of going in a linear fashion, just like a few of our toolpaths right there to sort of subtractively take out the material. And they then use human labor to just break it down, because this is also a good image to sort of compare the fact that machines can do a lot more than humans can, but what is the price we pay? Does it mean more machine time? Does it mean more time just prepping your files versus using labor and skilled craftsmanship that has been around for centuries? So I think this could also be something we'd love to talk about, because you're also talking about digital and physical, age-old and new techniques, and how we can sort of find a balance between the two. All right. The next star project is Wood Pavilion, that is like, I wouldn't call it a trend, but that's something ICD in Stuttgart, Germany is super interested in. And so to sort of compare the same process with different materials is what we'll also be looking into today. And you see that all of these robots end with the same condition of a circular disk, but what really goes on top of it, the end effector, is really what sort of makes projects like these possible. So what you see in front of you is the kind of setup that I showed earlier, which is what we'll be working with, which is a fairly simple servo motor with a drill bit right there. What they have added is also like a Dremel tool. I'm sure they had more tools to sort of pick and place all of these geometries. But also, we start about talking about architecture or enclosed spaces in layering systems. So what you see on the right here is actually sort of layered plywood, which houses these small little openings. So if this was in section, this would essentially mean it has like a pocket there to sort of house electricals and lights, but it actually comprises of 6 or 8 pieces of like glued pieces together right there. So yeah.
Speaking of the relationship between the components, the units. So there's one question: how related to the Armadillo Pavilion? How did they manage the joinery and edge conditions? So it seems that this pavilion had glue, so like the pieces were glued together. You might know that better than me. But the previous one didn't have any glue, right? It's just, as you mentioned, just compression and dry.
Exactly.
Reconnections.
Well, with this project, actually, so between, say, for instance, 2 pieces, they had a really small, like, lip, like, extrusion right there. So just imagine this with a little material right there, like about like half an inch or even lesser between. But this wasn't as a way to join the two, but instead use them as like register points, almost to align it in the right way. But all the forces that act in this project especially are all sort of compression based. So there is no gluing. So the only sort of supports that you see are these pieces right there. I think they had about 6 or 8, but yeah, it was pretty nerve-wracking to sort of bring this project to life versus something like this, where you start to have almost like puzzle piece joinery, which brings them together, but they're also kind of screwed together, which is why you see holes right there. So yeah, these are just smaller details of the project. What's interesting? Yeah.
It was my question actually about the edge
Am I
condition.
skipping all the
So
chat questions? All right, perfect.
yeah, so I like popped up that question in the chat. Thank you, Sarah, for like mentioning it. And I just wanted to know, like, the edge condition becomes very crucial when you're working with like, you know, curvy non-Euclidean geometries. So as you were saying, the edges are overlapping with each other, right? And the
Absolutely.
construction is like manual. It is not done through CNC milling.
Oh, this was CNC milling. Well, like robotic milling.
Armadillo.
That one wasn't. That was, oops, I'm just, there we go. So this one was primarily using a circular blade, which was numerically controlled. But so instead of this, if you imagine just, it's almost like using a 3D printer where instead of a drill bit, what they're moving is a circular bit. So it almost creates like lines versus this, which lets you create points or drill bits, drilling holes, and so on and so forth.
But when the panel will be connected to each other, the edges are not going to be flat.
Oh, with this project right there? Yeah, they weren't actually flat. They were all sort of inclined to accommodate the piece next
so
to it.
You need to adjust it like separately.
That's right. Yeah. So even when you see these sort of, I know they look like glitches, but they're actually really smartly placed bricks, which is why they're creating these shadows at the top. Maybe this is a better example of it. Perfect.
Great. Thank you so much, Missy.
Absolutely.
And the assembly process was all manually.
That's right. Yes.
That's incredible.
Yeah, that baffles me too. But I mean, using the same concepts, what we're trying to see through these projects is the fact that they go from circular cut stone pieces to robotically milled wood or plywood pieces. And what this facility, actually, this is in Madison, Wisconsin, and it's actually a stone company where they're using a few robots to sort of prototype products and work with architects on customized geometries, and also working as like buying and selling marble. So it's also like an interesting point in the industry where you're not just sort of being a buyer and seller of products, but instead sort of becoming a manufacturer and working between designers and production methods. So I don't know if you can tell the difference, but this has a huge drill bit right there, but it's also being shot with all this water, and that's primarily because stone is a much harder substance, and hence to sort of deal with all the heat that comes out of this process needs you to sort of be mindful of how do we actually streamline the process and cool the material and both the drill bit down. And why I'm toggling between this image and the previous one is that this is actually a 5-axis CNC milling machine. So it's not on top of a robot. It can do pretty much everything this machine can. The only difference is that this machine has the capacity to sort of do that. And if the rotary wasn't here at the base, it could also have potentially gone down and milled, except with just technical and you just the way you sort of weigh the material down, you wouldn't be able to get there. But even with the next assignment, I don't think we should use that as a limitation, but instead sort of project theories about how we can hold the material down from perhaps the sides and still use a surface underneath to go and cut. So that's one thing this robot could, and the next 5-axis CNC mill couldn't have done. And there's also a quick transition between the material, because you see something like stone, which is a lot more harder to deal with, versus something like high density foam, which is a lot more forgiving just as a material. We'll run through a few examples, but also just the fact that when you're dealing with something like stone or marble, or even like metals, when you're milling those, you have to sort of be mindful of all the tool paths. So what you see here actually suggests where the robot was moving to take all the material out, which also becomes like a language in itself. So with the next project, this was my matter design in 2015, partner between Wes McGee and Brandon Clifford. So what they're primarily doing with this project is trying to use huge chunks of foam and trying to mill it to sort of use that as formwork for GFRC, which is glass fiber reinforced concrete, to make a 3D assembly. So what you see on the right actually highlights the fact that all of these are like naked GFRC panels, which are placed on the outside. And these only comprise of about 6 pieces. So it also allows you to sort of get a better handle on like doubly curved surfaces. And I think this project was also dealing with how we can cool concrete and how it becomes an experience in itself. So what you see here, like all these random lines, are actually like copper wires, which have some water flowing through them, like both hot and cold water, to sort of regulate the temperature and sort of create an experience with the material. But so this is actually how, or like the inside shots of the project. And I'll run through a quick video that sort of showcases the entire process. What you see in front of you is a quick sneak peek of what we'll be teaching tomorrow, which is like wire cutting. So I don't want to actually steal the show with that, because it's an interesting process just by itself. But what's really happening here is this is easily like an inch thick drill bit, and it's huge because they're going to be at the time they were milling really big chunks of high density foam, so they didn't really need super small drill bits to get more precise geometries. So typically this happens when you want to take out the material first. So you care about the geometry, but not enough to really go with the final small tool to really detail it. So this is what they call the roughing coat, where you're primarily taking out just the larger chunk of mass out to get closer to your modeled geometry. So as you incrementally sort of move along the surface, that's how you're taking all the material out. And what's left behind, like you see these simple striations on the first half, they're called the roughing passes. So it's not the final product, but the first pass is just sort of done to take out all the key material that you know you're not going to need for sure. And then you go back with a much smaller drill bit, like maybe 1/8 of an inch, to really detail out your entire geometry so that it creates a seamless form.
That task could Bianco do it.
Absolutely. Yeah, we should totally. I was just speaking with Sarah about it. Maybe this was like a year or two back, but putting up a Dremel tool on Bianco to take out a smaller chunks of material would be perfect.
Yes, and also like this notion of really expanding the understanding of interaction between robot and different materials. I think it's very relevant. for the sake of education and like for like budget limitations, we use foam because it's cheap, it's fast, we can use the hot wire cutting. But I really like seeing these projects. It's interesting really to see how the materials are being deployed and studied. And also, you know, at this point with the knowledge that we have and the digital infrastructure that we have, you saw that the humans are fundamental, just like to connect the tests. Maybe it won't be like this in the future, we don't know. But yes, as you said, it's just like this notion of customization and really like getting closer to the matter, to the materials as much as possible and explore them. In that case, you can see that really, like, to me, it's crucial the fact that we are doing something in space, dealing with the material that we want to craft, but like the materials have different properties. So like the tool paths, the speed, all these components need to sort of like adjust accordingly. And so there needs to be this negotiation between all these elements, which I think that like the more we advance, the more it gets things complex, exciting, and just, yeah, like worth exploring.
Yeah, definitely. And with the robot, we've learned that it has so many parameters. You can move it in certain ways, but once you start dealing with the material itself, it comes with its own sort of set of possibilities and limitations. But just the fact that they interact together or a couple of days back, I was actually seeing a steam bending project where just the fact that thin slices of wood, when steamed or if we wet them, can be deformed a lot more easily. So then you are sort of leveraging these properties and sort of using a robot to almost like converse with the tool. And in a lot of ways, it also brings in that notion of how are we actually simulating each of these, because we'd like to see, or at least we'd like to know what to expect. But there's also a thin line between material properties and depending on physics simulation to sort of help us get as close as we possibly can. And which is why we'll be sort of try to simulate what we do today. But of course, because we'll be doing all of it manually, there are some boundaries to it. So what we'll primarily do with today's Rhino and Grasshopper script is use this robot. We actually never got to naming it, but let's just call it Bianco's big brother. And what's really happening here is this is a circular disc which could potentially sort of change the tools as and when needed. But it's a simple servo motor with a collet that houses the drill bit. And what we'll use today is what we call 1/4 inch ball mill. So I'll give you a brief introduction into like the terms that we'll be talking through mostly, but just for today's sake, we will look at two drill bits, essentially a straight drill bit, which has, whoops, that's really bad. But anyway, you understand that this is how it ends, versus what's on top of it is something that ends with almost like a circle. So if you imagine the material, the point of contact is a point, as against a drill bit like this, where the point of contact is actually sort of this distance. So it's actually a surface versus here with a ball mill, this is the point of contact. So it's just one point of contact. So I'll just run a quick video just to orient you guys with what the end effector looks like, and show a bunch of videos that are almost like close-ups to understand how the machine moves and how we'll be tool pathing the geometries. All right. Okay, so just to talk about some basics, I will take you through these two slides, which are primarily talking about what a traditional CNC machine is. So it's almost, I mean, it's the same concept of a 3D printer where you have your X, Y, and Z axes and a tool on top of it, which with a 3D printer is an extruder, but with a CNC mill, it houses a rotating drill bit. And there are a bunch of different drill bits, and all sort of correspond to different materials, different tool paths. Like the upshear sort of is used for softer materials, where as it's rotating around, it's taking out all the material. Just like that, it's pulling it up, versus the downshear is something you'd be using with say harder materials like plywood or certain stones, where you actually want to push the material down when you're actually milling it. The only reason I show this is to essentially understand the difference between a normal drill bit and something that has certain profiles, like compression drill bits. And what we'll be using today is something that is spherical at the tip of it. And
Mr. Sorry to interrupt, but
yes.
make sure also that you gave permission to all participants to take a look at the videos.
Oh, absolutely.
Yeah, because I cannot play them. So just for them for later, if they want, just to like when they think about the process and they want to rerun what you showed, make sure they can access this.
Perfect. Yeah. All right. So these are just the basics about the machine, the tool, and we'll talk about the tool path, which is how to actually use the tip of the robot to actually start creating tool paths, which is we'll talk about this primarily around two concepts, which is something like a contour operation is what we call this tool path, where entering your geometry, it goes in a certain sort of not a polyline or curve, but it has the same, well, simply put, it has the same start and end point. So that means as soon as the drill bit enters the material, it takes a circle, comes back out, as against something that is almost like a pocket, almost like a bowl, and that's the pocket operation on the right, which is primarily sort of entering what you want, like an object to be hollow on the inside to create these it's almost like creating saucers in it to take out all the material. And we'll talk more about this once we see 2 or 3 videos that show the entire process. But what we'll be using today's files is to do manual tool pathing to create your own custom geometries. But there are third-party softwares out there which help you with creating the tool path, so you don't have to sit and manually make these tool paths and really program the drill bit. But so this is just a quick snippet of PowerMill, which is very efficient with robots. There's also Mastercam versions and ShopBots, which a lot of the schools have, which have their own softwares. But this is just to sort of show you what the interface looks like. And so this is our robot, where we try to sort of take out material in incremental form. So what you see on the left is actually the finishing tool path. So you see like a smooth geometry coming out of it right there. But what it actually started with was a fairly rough geometry. So if I just pause right there, this is what we call the roughing operation. So if you want a geometry like this, we would do it in it's almost like a 2-step process, where first you break down your geometry into roughing paths so that you can really take out the chunk of the material. And this would all happen with a tool that has a squared edge. versus something like what's happening in the video happens with a ball mill, which does the exact same thing, except all our contour lines or the tool paths are so close to each other that you can hardly tell that there is a difference between the two. And that essentially happens with a tool that's spherical. So it also gives us higher resolution because this is the point of contact. So as you can see, so the image on the right essentially sort of captures the same quality, where you start with a lot of roughing paths to take out larger chunks, and then you go back and sort of smooth the geometry out. All right. Again, this is maybe a few days into it, or if you were to run this entire thing throughout, this would be maybe 2 hours into the milling process, where you see this geometry really quickly transition into the smooth form that was modeled on Rhino versus how it looked when it was first cut, just using its roughing operation. So I'll just toggle between the two images so it gives us a fairly good sense of what the before and after is. So you start with a lot of roughing toolpaths, which are actually spaced differently. So with a material like this, and this is not something we'll be getting into a lot of detail, but it's just good to know that when you do roughing passes, you can really space them out to like 1 to 2 inches if your material is as soft as foam, and really make the line sort of closer as you go up so that it gives you high resolution. So the image on the right is actually the end product, which is a really smooth geometry and looks fairly close to its Rhino counterpart. And this is the kind of tool pathing we'll be working with today. We'll actually be modeling the same exact geometry, where we'll try to, well, there are two things about milling. One is to model something and make something that looks exactly the same, versus programming the tool path and sort of trying to foresee what the outcome is, because what we'll be modeling here is the line, which you see on a larger surface right there. But all we'll be playing with today is a lot of lines at different offsets. So all of this changes, and depending on how close or far they are, that's how it sort of governs the overall geometry. So what's really happening here is that we're trying to mill out all the corner edges, because once you start milling something like this, it sort of enters the material. It goes in and follows this geometry, and then it exits out, and which essentially means you're left with corner conditions like these, which is why we went back and sort of modeled out another tool path, which was simply like the contour operation, which we just saw, where the tool simply goes and cleans all the rough edges up so that you have a finished product. Do we have any questions so far? Is the pace good, or am I going too fast? What do you guys think of it? Okay. See, one has, all right, perfect.
I have a question. So,
Sure.
For that model, we have to model the negative one for that's cutting, that's robot cuts that, or no, we have to model that's we want.
No, that's a great question. So in this case, the positive was being cut out, but what we'll be doing is the exact same thing. So it depends on how you're sort of introducing your component, because by the end of this exercise, we'll create one or two pieces that either in this case, I was actually just going to get to the next slide, which explains why it was milled in its negative sense, because it was used to cast this waste from an aluminum industry, which is like swarfs of metal. But with the previous projects that we saw, you're actually milling out the piece that you want. So with this exercise, we'll mill out the piece that we want and sort of model that and see how the toolpaths would work for it. Is that clear enough? Or maybe it would make more sense once I run through an example, perhaps. Yep. All right. So I hope this oriented you just well enough with the process to sort of understand that it's actually a rotating drill bit that runs along a line, simply put. But what we'll model today, I'll be starting with this geometry and walk you through how this was modeled, and also what its starting geometry was, because its starting geometry actually wasn't modeled in this way where it has these sort of niches, but instead it was a simple surface right there on Rhino, with which we sort of generated these tool paths. So I guess in a way, what I'm trying to say is it's a two-step process. With this exercise, we'll be modeling out a poly surface. And the second step is going to be sort of generating tool paths to create different patterns. So in reality, if we were to use the same script and just change how far or close they're spaced, we'd end up with different geometries which weren't modeled at first.
I have a question, Ms. Rick.
Mm-hmm.
If you want a nice and clean surface at the top, we want to use the other drill bit, isn't that? And pass it perpendicular to the surface.
That's exactly what we'll dive into. So maybe I should jump to Ryan at this point, but since we're in section here, I guess I could just walk you through it verbally. So this was actually used with, this was actually made with a ball mill. So if you imagine these curved ridges right there, if this was your drill bit, the point of contact was a point. So if the difference between these tool paths, I think at that point it was about 10 millimeters, like it was contoured at a distance of 10 millimeters. But if it was really fine, it would be so close that if it was, say, if it goes down to something like 2, it would essentially mean I would have a smooth geometry without any ridges. So that's something I'll leave up to you guys for when we start sort of diving into the tutorial.
I think there's an interesting question related to the difference between milling. So what's the difference between 2D milling and 6-axis robot arm milling?
Well, yeah, it's fairly straightforward. And to keep it simple, since milling is a new operation anyway, we'll stick with 3-axis milling, which essentially means that we'll be using the robot in X, Y, and Z direction for today's sort of tutorial. So all your contours would be sort of generated, and we'll be using that to create lines in X, Y, and Z planes, versus what happens with 6-axis is that this geometry could potentially be sort of milled. So if you imagine this to be the tool head, it would move along the geometry in something like this fashion. So you're not restricted by X, Y, and Z, but with 6 axes, you could, I don't know if my motion is clear, but you could essentially do that instead of a 3 axis milling machine, which can only do this. And what we saw with the foam and concrete project is when they were using a 5 axis milling, which again does that, but what the robot lets you do is also go underneath the surface. So that's the key difference between all 3 processes. Is there a follow-up question based on the different axes, or was I clear enough?
It's perfectly clear. I just want to be sure if that surface it was wanted to be that way, or if just it was about the drill bit that you had at the time.
Well, that's a great question. So with this, I was actually trying to test it for its acoustic properties, and which was sadly came to an halt because of the pandemic. But what I'm trying to get at is the increasing number of lines that you see here also mean that the surface in section isn't smooth, right? And smooth surfaces usually bounce off more sound. And a way to sort of diffuse sound is to create the corrugations almost in the surface. So that was actually the aim of the project, which is why you see that all of these have lines. And yeah, so these are actually supposed to be these metal panels, which are made from reclaimed aluminum swarf that you see in the texture, which is usually a waste material in manufacturing industries, which was clubbed with resin at the time.
Great.
Perfect. All right.
Another question.
Okay.
From Hania. I had experience generating G code for CNC machine woodworking. Each layer of the bull nose has to have a defined stepping going down in the material.
That's
I was
right.
wondering if the same situation goes for robot modeling on the robotic blade, or the robotic blade don't require to go down in several steps, or it depends on the material and not the machine.
It actually does stand true. So even when you're entering the material, if I just back up a little, and this is not something we have to be worried about, because sadly we're not getting to run the scripts, but also looking at the bright side, we can do anything on the computer. But what you see in front of you right here is what's really happening with how you actually enter a material when you're milling it, because it cannot just go straight down, because that's not recommended. You have to sort of ramp into it. So if I were to just show the toolpath, you, like the arrows go, you sort of ramp into it as a slow, steady step. You go around it and you come back out. And if you were to see the distance, there's a rule of thumb that the diameter of the drill bit, say for instance, this was 0.5 in diameter. So if it's a small object, like you see right here, if it's small and soft, like if this was foam, it would probably be okay if you go deep in the first half. Versus if this was something like MDF wood, you would have to break it down into a number of steps, because you have to be cautious of how much heat is being generated. And also at the same time, you have to be cautious that at the end of the day, it's a metal piece, right? It is stronger than a lot of other different materials, but also it has its own limitations in terms of how much force you can take. So in a lot of ways, it depends on the material. And to answer your question about ramp in and out, yes, that's absolutely true. It doesn't really matter if you're using 6 axes or 3 axes or 5 axes. This is a rule of thumb that is a good milling practice in general. But the good part is we won't be bothering a lot about this since we're working in the digital realm. But that's in the practical world, for sure, it would have to be, oops. And I think we're more or less done with, I'm just skimming through to see if we missed out on anything before I introduce this assignment. And Sarah, just jump in because I know we vaguely spoke about this, but I guess depending on how many troubleshootings we have to do, we could also tweak it, because I understand. But since we don't have to run the scripts, if the students need another day or two, like, guys, feel free to work through it, but it would be nice if you could come up with at least some kind of concept and a rough geometry tomorrow. So with this project, this was actually some of the student work from LTU last spring. And what they were essentially trying to do is make a wall with certain sort of components. And they were trying to mill out all of these components with foam, which is usually used for insulation, but they were also trying to use this as a mold to cast colored plaster. So what you see on the right are some previous iterations and 1:1 scale studies of the wall. And the second project was to create like this waffle structure, which was partly seating, partly acting like a canopy. And since this robot actually has like a working zone that is slightly larger than Bianco, that means we could run with dimensions of about 4 feet by 8 feet plywood sheets to use that as our starting material. But this is also a really good example because what the students did was they highlighted firstly the 3D model of it with a quick render, and they were also trying to sort of waffle out the structure in such a way that they could mill out a few details and talk through how the components actually come together. And that's one thing that would be super interesting if you guys dive into this. I think it's a great scale because at the same time we're still talking about inhabitable spaces and also talking about the specifics and details of how your projects would come together.
To me, Misri, like few slides back, just to highlight the fact that what we could, like the scale of the effort for like today is really to look at one component,
exactly.
Right?
Like a joint, if that's simple enough, or like
exactly
a panel, if that's simple enough. So, well,
yeah, go ahead.
Yeah.
And oh, sorry. Go
No, I'm almost done. I'm just I was just thinking if I skipped out any points, but yeah. So even if we talk about, say, an assembly of 3 pieces, that's good enough. We can look at larger scales as we approach the end of the workshop, but it's good to sort of think of a larger scale and say, okay, we're picking out 2 or 3 objects. So that would be perfect, just so we can spend some time talking about the details of it. And just like yesterday, the file has already been shared on the drive. I can walk you through that. And the same kind of deliverables with what we'll be doing, or sort of putting in images or simulations if you possibly can, that would be perfect.
So are you showing us the Rhino file?
That's
so
right.
That we can see the demo and we can look at the toolpath and yeah, so the same format, right? Like you decide what you want to show. We have seen that you guys are skilled in terms of communication. So you decide how you want to explain what you have in mind and try to imagine even like a small scale assembly or like larger scale kind of a concept idea based on this technique.
Yeah, for sure. And feel free to reach out if you have problems, or we could also talk through like concepts, and you could develop that over the week. That's not a problem. Can you guys see my rhino and my grasshopper? Okay, perfect. All right, so before I jump in, I think it would be super helpful to, oops, there we go, to actually dive into some of the specifics. And Espartaco, this is something that overlaps with the question you just asked, because when you imagine a drill bit that is almost like cylindrical or has like a semicircle at the end of it, and you imagine that move over, say, regular offsets of certain distances, this is the kind of geometry that I was playing with at the time, which is why they had like these niches in it. But as soon as you start bringing them closer, it starts to approach a very smooth material. And the closer you bring them, the finer the line becomes, right? Because in a lot of ways, it's about this object sort of moving like that and sort of being picked up. So if I were to really zoom in, what we'll be dealing with today is, this is the robot head, and this will be your geometry. And in section, what it's doing is it enters, which is what Alina, I think, was that the question from her? So which was basically asking if we have to ramp in from a certain point, whoops, which was, you approach the material, you enter in, you go through all of these, and then you bring it out, is what the concept of today's project is. So I'll just run through the script that I have modeled out already. And this is the same geometry we saw in our videos. So what's really happening is that this script is sort of divided into 3 or 4 parts. And what we care about is this poly surface. So this is the geometry that is being used, and all it's really doing is it's running between 2 paths. One, the first group actually deals with the tool path, which deals and sort of helps you create these contours, either closely spaced or sparse. So you have the density of it, which can be played around with. So in this case, all of these lines are actually 5 millimeters apart. So we're trying to sort of, let me just put this back, because we're also trying to simulate. Oh, no way. I hope my Rhino doesn't crash on me right now. I was scared of doing that. All right, this is something you should not be doing, simply because I was trying to simulate that at the same time. And because I moved the geometry, it was going through all of this to give me an output which looked something like that. So if you look at it closer, this almost kind of resembles what was seen with the piece that we saw towards the end of it. So before I do anything else, let me just shut all of these. That should make my life simple. And yeah, so this was the core geometry. So everything else could actually just be hidden. So what's really happening is, this is a geometry that only comprises of 2 planes. This is plane 1 and this is plane 2, and they're both sort of joined together. And what we're playing around with is, how do we contour it? And to do this, it's a simple contour operation, which sort of divides your geometry into a bunch of lines, which can be played around with in the contour density. So as you increase the density, you see that we're generating a lot more lines. So the higher, the smaller the number, the closely spaced lines you're able to achieve. There we go. So if I were to really sort of zoom in, these are really closely spaced, which means if I were to mill it, it would most certainly be like a smooth curve. And so depending on how I'm changing this partition between the lines, that's how far the lines are, and hence you can
Yes,
sort of get
but
those striations.
clearly it will increase the time too of
Absolutely, yes. Milling is actually fairly, I mean, it is a time-consuming process. I don't even feel like I should sugarcoat that, but it does consume time. There's also that factor of you starting with a block of material and only getting out certain geometries. So there have been, well, not concerns, but definitely discussions about which one is better. Is additive better? Is subtractive better? But it really becomes like a project specific conversation. But yeah, if we could definitely debate about this after we do wire cutting, because then we would have seen 2 or 3 different processes to sort of talk about efficiency and material and waste and so on and so forth. So coming back to our contour operation, it simply sort of breaks it down into smaller geometries. And now what you see on the right is very, very similar to what we've been doing with the first 2 assignments, which in a way breaks it down into its planar form, right? So all these lines that you see in front of you are actually X, Y, and Z. And the same kind of logic is repeated for all the points that you see here. And an extra step that wasn't added in the previous ones, but we have to be mindful of that here, is that all of these sort of gumball-like things that you see on the screen are happening on the geometry, which is fair, but it's also happening upstairs. And why so? It's primarily because if you were to imagine a block of foam right there. So if this was your material, and what you were actually doing is consuming the material and entering it right there. So you start with the robot, you enter the material, you mill out your process, and then come back out, right? Because you don't want to be entering at the wrong spot and coming out at the wrong spot. So I don't know if this is clear enough, but let me just run this through the simulation so that it does some justice to what the actual procedure is. Because what's really happening is if I go back to my home position, it's like the same concept of Bianco, where it starts from the home position and it goes to its first geometry, which is right there. And as I skim through this, we're gonna see that it's approaching this point first, and then it goes down. So we're actually asking the robot to sort of orient itself in Z height with the first point right there. So when you're actually running the file, it's a 3-step process. Well, actually a 4-step process. So this is our point 1. It goes down before it enters the material, which is point 2. It runs, in this case, it's only running at an angle. So it reaches point 3. And then it's sort of asking the robot to come back out, which is point 4. So just keep your eyes out for the first process, the first toolpath rather, where it's entering, it's traveling, and then it's coming back out. And this is also like a continuous process. Like in this case, it seems to be running all toolpaths before it comes back out. And that's primarily because we haven't actually flattened all our curves. So since all our curves are flattened in this case, it's doing all of these simultaneously, before it comes back out towards the endpoint. So it enters with your first curve and sort of exits out with, say, the last curve. And we could also have changed that, but since we're sort of working on our digital files, we don't actually have to be concerned about the fact that it isn't coming up. But if your geometry actually requires you to just make a hole and come back out, we can definitely do that. So I'm just gonna, for the sake of seeing this entire process, I'm just gonna bring up the number to, say, 50. So you see just a few curves, and that way we can look at the entire process. So currently the robot is approaching its first curve. There we go, and it goes down. It finishes the toolpath, comes back up, then it goes to the second one, it finishes the toolpath, and it comes back up, and it goes to the next. So what's happening here is it starts from point 0 to 1 to 2, because it's coming back up to clear the material. It goes to 3, 4, 5. And what's happening here is we're also trying to optimize the process a little. So we could have done 1 and 2, but since it is at on the other end already, we just much rather have it start from the other point, if that makes sense. And
why the tool center point is not at the end of the drill? I don't know if you covered that already. Does it matter? Like the 3 axes on the effector, why are they in the middle? Is there for the visualization?
Not really. At the time, I was also toggling between a few drill bits. So based on how deep your drill bit is on the tool, it makes sense to sort of and the material at the time, it makes sense to sort of align it with your material instead of sort of aligning it with the virtual space, because well, it's funny that the floor there wasn't fully leveled, so you always see discrepancies. So this is here instead of being further down is because that's how precision, or like recalibrating the tool with the real space at the time. But yeah,
interesting.
Yeah, it's ironic because then we talk about digital fabrication and there are hiccups with that. But yeah, that's almost always the case with construction sites too. Like nothing really comes to its millimeter precision. But I'm also hoping this kind of gives you a fair sense of how much it enters the material, because then we're trying to consume all of those lines as geometry that is being sort of milled out. But also at the same time, if we try to create a version of this in 3D space, what the second part, or what's happening on bottom left, is actually just a simple simulation of the geometry, where what I'm essentially trying to use these toolpaths, create a circle at the end of it and extrude it so that these become like geometries itself, and so on and so forth, and just Booleaning it out. So in a lot of ways, it's not computer generated, because third-party softwares actually show you how to toolpath complex geometries. But what we're trying to do here is really get into every detail that we could possibly change about this project. All right, so for the sake of understanding, I have moved this geometry a little ahead of us. And this is how it's aligned with the geometry. So it's almost like imagining this drill bit, which is a ballpoint. And if this was your tool, it's almost like it's consuming out this much material with each pass. So what it's doing is simply sort of extruding a circle along those lines. So for now, our distance is about 25, or I think I put it to 50, but that's how close it was before. And then you're also going to reach a limit where if they're too close, what really happens is you start to sort of see really smooth geometry when it's super close. And that's something that we looked at in this diagram right there. So what we're really playing around with is sort of how dense these lines are to get as close we possibly can to the geometry, or actually instead of wanting to get closer to the geometry, if we were to actually predict how far we want it, we could actually use it as a material texture in itself. So the first half of the script mainly models these small cylinders across. So you can see that this is how the toolpath is kind of going through most of it. And if you Boolean it out, this is closer to what your geometry would look once you actually take out all that material. So if we were to, again, if we just disable this, and if this time I'm decreasing all the toolpaths, you're going to see how closely spaced it is. And then we can try and see how the simulated version of it looks. All right, while we act patient with the technology, have you guys tried to download these files to give it a pass?
Yeah, and I was noticing that do you always have to apply that shift in the list in which you have like basically changing the direction of the
So
lines?
what that script does is, and we could get rid of that too. So what it simply does is, since it's entering, it's going, and it's on the other side already, so it sort of reverses the list and merges the two. That's one way to reduce some machine time. But I mean, with a geometry this small, it's negligible. Like if you were to make 500 copies of these, then it would save quite a bit of time. But if it's just one or two pieces, it doesn't matter if you go and you come back to the first starting point and then enter the toolpath again versus flipping the directions.
Okay, so it's for the sake of optimization.
Yeah.
When you want to do these things.
Yeah. Just because you're closer to the exit point of the first toolpath.
Gotcha.
All right. Do we have more questions from the students?
Or at the moment, we don't have specific questions in the chat log. So what would you suggest for them to do? Is like, would you like them to work on a pattern on a surface, or would you like them to cut, some
I think it would be great
objects?
to sort of, like model one piece out, and we could look at the toolpath for that, or see how sort of contouring it gives it textures, if that's the intention. But maybe it would be a good exercise for you guys to come up with one piece that can be aggregated in almost like a wall assembly. But yeah, so as simple as let's keep the work as simple as creating just one geometry, but which can be replicated if we were to sort of make like 50 pieces with it. How would they come together?
Like a tile.
Yeah, almost like a tile.
Yeah, and I would say try just I'm encouraging you like to try to work in 3D. It's like try to cut to create something that really expands in the space. So instead of having just a flat object on the XY plane and just cut it out, I mean, we know that we can do that. Try really to build complexity, even like keep it simple, but like try to incorporate these things that Misri was talking about through the presentation that I think was very insightful.
I'm just waiting for this to respond to me, but did that give you a fair enough gist about the process? Or after seeing the videos and sort of seeing how that sort of replicates in the digital space, was that clear enough? And we'd be happy to share more sort of examples from like contemporary research practices, because not just looking at foam and wood, but like practices around the globe these days are milling all kinds of materials, which has its own sort of design capacities, which is really interesting to see.
Mr. Do you want me to run the KUKA PRC core? I just opened your file. Actually, I was following you. But if you want, I can run the simulation here.
Sure.
It's just that you wanted right now.
That's right. Yeah.
So we can see this and you can talk about this if you want.
Perfect.
So let's go back. I should have flattened already. We should just be good to go. Let's see what happens. And I'm sorry, I'm distracted because I'm seeing Bianco working. I don't know if you guys can see Jeff and Emily's webcam, so that we have your your light drive files in progress. So you will receive them soon. But yeah, sorry, I distracted you from this, so we can just see.
Let's switch the audio.
Here, I just muted mine.
Is that better?
Yeah, that's better.
All right, we got through 4 of the ones that were in the reviewed by Sarah folder.
Great.
So you just have 1 left. They're looking good. Way to zoom without.
Okay, we'll see. Let's keep that for the moment which you will upload them on Drive. But we're looking forward to seeing them. Thanks.
Just wanted to check in while everyone was still there.
Did everything work all right?
Yeah, everything has been working pretty well.
Okay.
Yeah, no errors in the codes or anything. It's been real smooth.
How about the one with many points?
We did that one first. No problem.
That worked. Was the geometry close enough to the simulation? Because I removed some points when I checked the file.
Oh, you did? Let me go back and see.
Well, we can consider. That's what I'm saying. Like to.
Yeah, it's pretty good.
Okay.
Yeah, I'd say it was reasonably close. I think that one had something like close to 600 lines of code.
Yeah.
The file that we ran.
Yeah, there were 1,500. That's why I reduced them a little bit, just because I wasn't sure.
Hey, we've never actually seen the limit, by the way. You say there's a limit, but we haven't seen it yet.
Okay, it's from the. I think we
just
tested
about how heavy the file could get, right? About 65 KB. I might be
exactly.
wrong.
No, you're right. That's exactly the number. That's why I tried to reduce the file.
65 kilobytes. Is that what you're talking about, Misri?
Correct.
Mm-hmm. Yeah, I think it's about 65 to 70 KB is what we're sort of expected to stay within.
Okay.
Yeah, but I can try to increase the points. And
yeah, either that. I mean,
file.
there are always ways to split one file into 2. That's just extra effort.
Yeah.
Get it back in time. If it's a long exposure shot, yeah, that's that's a concern. But I think the image is actually, from what I can see in that small little pixel there, looks fabulous. Yeah.
Get it without the glare.
Oh, wow, yes.
That's really great.
Screen.
Yeah, maybe Sarah, we should spotlight Jeff's camera so that the students can see it.
Yeah. Let me pin you for everyone. Here it is. Yeah,
the
I
focus
think
is terrible.
Yeah.
Yeah, so we got some good ones. That was not great. That one was okay. We were playing with some light. Here's this one.
Nice.
You know, we had to play around to get the exposure right on several of them. This one you can't really see on screen because of the density, but it's a good picture.
Nice.
Anyway, yeah, one more to go for the first batch that you checked, and then we didn't really look at any of the others yet.
Yeah, there are some more submissions, and if we have time, I'll try to increase the amount of points of the previous one, and try to reach this so-called limitation.
All right.
All right, that's very promising. Thanks, Jeff.
Yeah, sure.
Yeah, thanks a lot. Thanks a lot. And we are trying to do this for the hot wire cutting process as well.
Perfect. Yeah, I wish we could use the robot at Ballard.
Ah, that's true. That's true. But
right.
yeah, so we have a couple of minutes. Jeff, what is he doing with the light? So we have one question. Our drill should always be set perpendicular to the surface? Question mark.
Yes. So, I mean, there are ways to actually make it move along the surface. That also makes the simulation slightly more complicated. So, for the sake of sort of scratching the surface and understanding the basics of this process, I think it's good if we limit ourselves to like 3 axes. But by all means, don't let this sort of stop you from saying, okay, what if we were to mill it and then we flip the piece and we mill it? So then in reality, you're trying to actually mill also underneath your geometry, which should allow you to explore a lot of different variations.
And again, this time is just visualization. You can, export an animation. You can record the screen.
Or just like diagrams of if the same tile was multiplied, what that would be like. But
exactly. So there's no need to export the script because this time
exactly
is just for the constraints of the tools and people involved in this. Yeah, but and so drop your thoughts in the Google Slides folder file and try to just imagine a process. And as Lisa was saying, try to imagine one unit and try to imagine what it means to assemble it and to create a sort of idea of tectonics. It creates a more volumetric entity.
Yeah. And also, I mean, the good thing is if we're not running the scripts, we don't have to really bother about having to be fair to the material. So I guess in a lot of ways, you could project your geometry as being cut out of stone, cut out of wood or foam, or cut it out and say, okay, what if we were to cast concrete in this? So I guess we don't have any limitations also in terms of how your proposal with the materials works. I guess it could also mean we can explore a palette of different materials.
Yeah, and even like tomorrow we can discuss, we try this, just keep in mind that like if we were to run this script on the specific material, the best approach would be this, or like the best way to tweak this would be that. So I mean, we'll discuss this, but not necessarily you have to worry about in this phase.
Hello, I have a question. One question
bounding
about.
Box?
Mm-hmm. Well, the bounding box would be 4x8 as like a normal off-the-shelf plywood sheet. But in terms of thickness, you can go up to 5 or 6 inches, not a problem. I think at this point, I'm also open to you guys exploring the extents of how big it can get, because this robot is fairly huge. So in a lot of ways, it could also allow you to make larger geometries, almost like the scale of the pavilions that we saw. So the
Is
work,
it 4 feet or 4 meter?
4 feet, 4 feet by 8 feet
Okay,
is,
great.
yeah, perfect.
So I think there was, I have a question. Yeah, go ahead.
Hello. I have a question about, for instance, if I want, I have a cube and I want to mill out the subtraction, the subtraction, and can you help me with the script? This Grasshopper script, I see that you go straight to the triangle that go straight to that path. And if I want to mill that RAM, how to generate that RAM path?
What do you mean by the ramp? I'm just trying to.
It's like you have a cube, a perfect cube, and you try to generate the RAM to engrave the shape that you gave us, this triangular this triangular shape. How to generate that?
Let me just pull up the file super
Yeah,
quickly.
I think is it related to what you showed earlier, like the little, like the twig that does the drill to get to the first point? Because in the file you're going directly to point 0, right? Like straight down instead of like doing that thing. I believe that is that automatically generated by PowerMill, Misery?
Not necessarily, but oh, you mean if we were to add this with our Rhino file, we would have to add it, or at least script it that you say, okay, you enter at an angle and then sort of start following the toolpath. But with traditional CNCs, PowerMill actually does it for you, so you don't have to think about where to enter or exit. But it does give you that option of, if this is your geometry, where would you like the ramp to be on the perimeter, is what you can control with things like PowerMill, or even like CNC, like Mastercam, which is used for a traditional CNC machine. So actually, sure, let me see if I can pull up that exact same video, and I'll be sure to sort of. Here, Sarah, can I share my screen super quickly?
Yeah, absolutely. It's just the video is pinned, but you can share.
Perfect. All right. So what's happening here is, since these are really huge, just the dimensions of these drill bits, you're going to see that it takes out a lot more material. And also the way it enters the geometry and sort of continues to mill it without picking itself up is something that these machines and the softwares they come with allow you to do. So we don't have to actually script any of that with a traditional 3 or 5 axis CNC machine. So it continues to sort of keep milling until it's done with the toolpath without actually taking a break. So all these faint lines that you see on the surface, and you can also see the depth at which it's sort of entering the material, simply because it's also a really soft material. So it's okay to start consuming that much.
So did you actually use your script from Grasshopper to produce those tiles, those aluminum tiles that you showed earlier, or this is a demo, but then you programmed this with?
Oh no, this is all made with this robot, the same robot we're scripting with.
Okay.
Yeah. So the script that I've shared with Rhino and Grasshopper, that's exactly what was used to make a product like this.
Okay, so in that case, it's okay if you follow like that point list.
Absolutely, yeah.
Okay, that's mean if you have a complex sculpture like, and you can go directly to that surface, it's no problem, right?
Yeah. Yes. So if it was super smooth, like this is, I think I was toggling between this image and this one simply to show how we can, in a way, use the toolpath as a design intention instead of expecting a geometry that exactly matches your 3D model, which is the case in this case. Because it really gets as close as it possibly can to the 3D model, because the contours here are so close to each other that the finished product is a very smooth surface as against a geometry like this. But again, if you compare this in terms of milling time, this took at least like 4 hours, and what you see in front of you here took about like 3 minutes. So it's not even comparable in terms of which one is faster, or what. I guess it depends on what you're trying to achieve with that object, whatever you're designing, to sort of say, hey, I think this is what my proposal is, and to achieve this, even if it means I'm at the machine for 5 hours, it's worth the time. So and with this simulation, I think that's one great bullet we dodged very gladly, right? Because then you don't actually have to be right there, but use the simulations to sort of tell a story.
Yeah, thank you.
Absolutely.
Yeah, of course, we're still available if you have other questions.
I have one question, Sarah. It's with you, like regarding KUKA PRC. It's about start position. So as like you demonstrated, the start position shows like a button, but in my like version, it is not. Like when I go to advanced, the initial posture says like numbers 0, 1, 0, 1, 1, 0, 0, 1, 1.
How should we deal with? Do you want to share your screen so that we can see?
That would be,
we can fix it. And then just a general comment. As long as we approached the 2 hours, guys, if you didn't have time, to finalize the second submission, you just submit later. Like we'll spend time in the future processing your submissions and to promote them. So don't worry. I mean, there's room for you. Okay, so let's start. Well, what do you want to do first of all? Because the thing is, a start should be, if you apply before exit, that should be just the default. So when you slide back the slider to 0,
it is at 0.
You should go. Oh, that's the thing. You should do the simulation. Okay, perfect. Go back.
So that's 0. So I want my start position here.
Okay, so open KUKA PRC. Ah, interesting.
And this one has these numbers.
Why you have that? Wait, let me see. Do you have version limited? Let's solve this via email. Do you have like the version that I sent to you?
No.
That is shared in the.
It's on the
I installed it separately from Food for Rhino.
Ah, okay.
Or do I need to use the version that you shared?
Is more recent. Okay. It should be straightforward. Just install it, and you have a bunch of new options and new features.
Great, thank you.
You can use. Yeah, and let us know if you have questions. Just shoot an email, and we'll try to solve this. But absolutely. Sure. Yeah, thanks for sharing.
Stop the share.
And
I wonder, in this workshop, could you show us how to calibrate the tool? Because when I try to calibrate the tool and with my robot, I always quite messing with the world world XYZ and tool ABC. That thing is quite I don't know how to say quite not
challenging.
No worries.
yeah. It's not really easy to understand that it's A, B, C, and then X, Y, Z, and in this space, it's really hard to understand.
We can think about something. Yeah, sure.
Yeah,
sure.
we could set up a quick example with our next class or something if that helps.
Okay.
Yes, cool. in digital, it's fine. I need to ask our heroes in the B Lab, Jeff and Emily, if they could record another demo, like similar to the one that we saw with Emily was using the Teach Pendant, and then Jeff showing you like the script running in the Teach Pendant. We can do a version of that in which we are showing you how to set up a tool. Yeah, that's feasible. Let us know. Like we need to coordinate this. We didn't include this in the content, but.
Yep. And just to clarify, did you mean setting up the tool in the like setting up that mesh as a custom tool in the Grasshopper script?
No, I mean when you set up the actual tool in the KUKA robot.
All right. Okay.
And there are two elements. One is called mastering, and that's something that we won't share because it's something that you do like when you set up the tool, and that's deals with like positioning the zero exactly at the origin so that like it matches with what you have in Grasshopper. What we can share though is how to set up in the Teach Pendant in the robot the tool, so that when you export the script, then the robot recognizes, the tool number, the rotations, and can find the values of X, Y, and Z, and the rotation that you were mentioning. So these things for sure, those are things that we can share with you guys. Yeah. Thanks for mentioning that. Yeah. We'll try to make it work.
Yeah, thank you.
So many questions today. I'm excited.
Yeah, I'm really excited.
That you guys are.
Also, towards the end of it, I'm really hoping a few people agree with a few workflows and a few don't. So at least we can have a discussion based on why we're doing what we're doing, and even better, what we could potentially sort of project with the final assignment for sure. Just to get your brains running in terms of what we can do with this too.
Absolutely. Yeah, and we like this kind of conversations. Hopefully there will be room at the end, like the last day, we really can share our ideas related to this. So I think other questions?
I thought Jeff wanted to say something.
Oh, hi.
We're good? Perfect. Okay.
We turn the lights on.
All right. It's just. All right.
Okay, so I just would like to stay a bit longer with you and Emily. So I think we can call it a day. I would like to keep the streaming going with the light bright exercise, unless you guys are done. If you're done, then it's fine.
Well, we would have to look at the new files that came in.
Okay, well, we can discuss internally this, but I think that we can just thank the attendees. Thank you guys for joining us today. Thanks for your enthusiasm, for your questions.
Looking
see you
forward
tomorrow.
To tomorrow. Yeah, that should be exciting.
Yep. And so the schedule will be the same. We discuss the submissions and then we kick off the next hands-on, the next assignment, which will be outwire cutting. And we have tomorrow, right? Guest lecture.
Yes. So Matias Del Campo will be joining us tomorrow and sharing his insights because he's extensively worked with robotic fabrication and done some class blowing techniques with a robot, I think. And most recently, he jumped into AI and machine learning to generate computational workflows and plans and all sorts of exciting things. So we're hoping he joins us for a little bit and speaks with the students, and we can have a quick discussion and continue that conversation even after he share some insights and continue with hardwire cutting. So I guess we'll be juggling quite a few balls tomorrow with a bunch of different conversations.
Great. So it's going to be exciting. So thank you, guys, and we'll see you tomorrow.
Perfect. Thank you.
Thank you, guys.
Thank you. Bye-bye.
Bye, guys.
Bye.
See ya.
See you. So meanwhile, Jeff, what would you prefer me to do? Should we keep streaming, stop streaming, but we have a powerless Zoom? Or just we chat?
Do some practical talk, I guess. We just need to figure out what the schedule is going to be like for completing some of the things. The files today all ran well.
Nice.
I'm excited to share some pictures with everyone. Other thoughts? Let's see. Question about like, obviously we missed seeing what you all talked about today, lecture-wise. The videos will be posted. Like the YouTube videos will be posted, or the recordings will be posted somewhere. We can take a look. I'm just curious, like, you know, the way you talked about things, and for the next part, and the CNC and sort of the CNC reductive stuff with a mill bit.
Yeah, I think the recording should be up for sure, and we're also sharing that with the students. So yeah, and you guys, I assume, are already on the drive.
Yeah, they have. Perfect. You guys are in the drive. There's
so
a folder.
Have all access to it.
Yeah, with the Zoom recordings, plus it will be streamed on YouTube, so you can have access to all this. Yeah, actually, let me close this, and like another final thank you to everyone. Thank you for following. Thank you for joining us.
It's been a pleasure.